Right now, as you hear these words, you believe you're experiencing a moment called the present. You think the past is gone forever, the future hasn't happened yet, and time is flowing like a river, carrying you from one moment to the next. But what if everything you've ever believed about time is wrong? What if the present moment is an illusion? The flow of time is a trick your brain plays on you, and past, present, and future all exist simultaneously in a timeless reality. Scientists at the cutting edge of physics are discovering that time, the most fundamental aspect of your existence, might not actually exist at all. The ticking of clocks, the aging of your body, the sequence of your memories, even the very concept of now, might be elaborate illusions created by the way your consciousness processes a reality that is fundamentally timeless. Make sure to hit that like button and subscribe, because we're about to journey into the most mind-bending discovery in modern physics. We'll explore how Einstein shattered our understanding of time, why quantum mechanics suggests the universe has no universal clock, and how leading physicists are proving that what you call time is nothing more than a persistent illusion. What we discover will change how you experience every moment of your existence. This isn't just about abstract physics. This is about the nature of your reality. If time doesn't exist, what does that mean for free will, death, memory, and the very meaning of existence itself? The implications are so profound, they could reshape human civilization's understanding of what it means to be conscious beings in a timeless cosmos. Prepare yourselves. We begin. Every morning, you wake up believing you've traveled from yesterday into today. You check your clock, plan your future, remember your past, and live in what feels like a flowing present moment. But this entire experience, everything that makes you feel like a being moving through time, is constructed by your brain from something far stranger than you can imagine. Think about this moment right now. You feel like you're experiencing now, but what exactly is now? Is it this word you're reading, this sentence, this paragraph? The more precisely you try to pin down the present moment, the more it slips away, like trying to grab water with your hands. Neuroscientists have discovered that what you experience as now is actually your brain's reconstruction of events that happened milliseconds ago, stitched together into a seamless narrative of temporal flow. Your brain is constantly creating the illusion of time through incredibly sophisticated information processing. The temporospatial theory of consciousness, developed through cutting-edge 2024 research, reveals that your sense of temporal flow emerges from neural activity across multiple timescales, from milliseconds to several seconds. Your consciousness doesn't experience time directly. It constructs temporal experience by integrating information across nested hierarchical networks in your brain. Consider how your perception of time changes based on your mental state. When you're bored, minutes feel like hours. When you're engaged in flow states, hours pass like minutes. During emergencies, time seems to slow down as your brain processes more information per unit of clock time. These aren't just subjective quirks. They're clues that time, as you experience it, is a construction of consciousness, not a fundamental feature of reality. The most shocking discovery is that your brain creates temporal experience through what neuroscientists call cinematic, extensional, and retentional models working together. Your consciousness doesn't experience a flowing present. It experiences discrete moments that your brain stitches together like frames in a movie, creating the illusion of smooth temporal flow. The present you think you're experiencing is actually a reconstruction of multiple past moments integrated by your neural networks. Cultural anthropologists have shown that different human societies experience time in radically different ways. Some cultures have no concept of linear time, experiencing reality as cyclical or even timeless. The fact that humans had to invent clocks, calendars, and schedules suggests that precise temporal measurement isn't natural to consciousness. It's an artificial overlay we've imposed on a more fundamental, timeless reality. But the illusion goes deeper than individual perception. Our entire civilization is built on the assumption that time flows from past to future. We make plans, set goals, feel regret about the past, and anxiety about the future. We age, we die, we measure progress and decay. Yet what if all of this is based on a fundamental misunderstanding of reality's true nature? Recent research in consciousness studies reveals that even your sense of personal identity through time, the feeling that you're the same person who existed yesterday and will exist tomorrow, is constructed by your brain's narrative systems. The you that experiences temporal flow might itself be an illusion created by information processing patterns that have no fundamental relationship to time as physics describes it. In 1905, a young patent clerk named Albert Einstein destroyed humanity's understanding of time forever. His special theory of relativity didn't just modify our concept of time, it revealed that time as we experience it is fundamentally illusory. What Einstein discovered was so shocking that we're still grappling with its implications more than a century later. Einstein's first bombshell was time dilation. He proved mathematically and experimentally that time passes differently for observers, moving at different speeds relative to each other. This isn't just a theoretical curiosity, it's measurable reality. GPS satellites orbiting Earth experience time slightly faster than we do on the surface because they're moving at high speeds and experiencing weaker gravitational fields. Without correcting for these relativistic effects, GPS would be off by miles within hours. But here's what will blow your mind. There is no universal now. The concept of simultaneity, events happening at the same time, is completely relative to the observer. Two events that appear simultaneous to you might occur at different times for someone moving relative to you. This means there's no cosmic clock, no universal present moment that defines now for the entire universe. Think about the implications. Right now, as you read this, there is no universal right now that extends across the cosmos. Your now is different from the now of someone on a moving train, which is different from the now of an astronaut on the International Space Station. The present moment, the thing that feels most real and immediate to you, doesn't exist as a universal feature of reality. Einstein's general relativity made the situation even more bizarre. Gravity doesn't just bend space, it bends time. The stronger the gravitational field, the slower time passes relative to weaker fields. Near a black hole, time dilation becomes so extreme that what feels like minutes to someone falling in corresponds to years passing for distant observers. Time literally runs at different rates in different locations throughout the universe. These discoveries led Einstein to a conclusion that haunted him for the rest of his life. The distinction between past, present, and future is a stubbornly persistent illusion. In Einstein's universe, all moments in time exist equally. The past hasn't disappeared, the future hasn't yet come into being. They're all equally real, equally present in the four-dimensional fabric of space-time. This view, called the block universe, or eternalism, suggests that reality is like a loaf of bread, where every slice represents a moment in time. All the slices exist simultaneously. Your birth, your death, every moment of your life exists eternally in this four-dimensional block. What you experience as the flow of time is just your consciousness moving through or becoming aware of different slices of this eternal, unchanging structure. The block universe resolves many paradoxes in physics, but it creates profound philosophical problems. If all moments exist equally, what happens to free will? How can you make choices about the future if the future already exists? What does it mean to say someone has died if their moment of death exists eternally alongside their moment of birth? Modern physics has confirmed Einstein's insights with incredible precision. Atomic clocks can measure time dilation effects from walking up a flight of stairs. Particle accelerators routinely observe time dilation in subatomic particles moving at near light speeds. Gravitational wave detectors like Ililigiosu measure ripples in space-time itself, confirming that space and time are unified into a single, flexible fabric that can be stretched, compressed, and warped. While Einstein showed that time is relative and flexible, British physicist Julian Barbour has spent decades developing an even more radical idea. Time doesn't exist at all. According to Barbour's revolutionary theory, what we call time is nothing more than a measure of change, and change itself creates the illusion of temporal flow in a universe that is fundamentally timeless. Barbour's end-of-time theory proposes that the universe consists of an infinite collection of possible configurations he calls nows, complete instantaneous arrangements of all matter and energy in the cosmos. Each now is like a snapshot of the entire universe at a particular configuration. These nows don't exist in time. They simply exist, timelessly and eternally, in what Barbour calls Platonia, the space of all possible configurations. Think of it like this. Imagine every possible arrangement of chess pieces on a chessboard. Each arrangement exists as a mathematical possibility, regardless of whether anyone has ever actually arranged the pieces that way. Barbour suggests that reality works similarly. Every possible configuration of the universe exists as a timeless now, and what we experience as the flow of time is simply our consciousness becoming aware of a sequence of these configurations. But why do we experience these nows in a particular sequence rather than randomly? Barbour's answer involves what he calls shape dynamics. The configurations we experience as connected in time are those that are similar to each other in their overall structure or shape. Our consciousness follows paths through Platonia that connect similar configurations, creating the illusion of smooth temporal evolution. This explains why we remember the past, but not the future. The nows that feel like past to us are those that contain records, memories, and traces of other configurations. The now you're experiencing right now contains memories of yesterday, photographs from last year, geological records of ancient events. These aren't traces of things that happened before. They're simply features of this particular, now that create the illusion of a past. Barbour's theory makes testable predictions. If time is truly emergent from change rather than fundamental, then the deepest laws of physics should be expressible without reference to time. Recent work in quantum gravity and cosmology has found exactly this. The most fundamental equations describing reality, like the Wheeler-DeWitt equation, contain no time parameter at all. The implications are staggering. If Barbour is correct, then causation, as we understand it, is an illusion. Events don't cause other events to happen later. Instead, configurations that appear causally connected simply exist as related nows in Platonia. The Big Bang didn't happen before the present moment. It's simply a now that contains fewer records and traces than the now you're currently experiencing. This resolves many paradoxes in physics. The problem of time's arrow, why time seems to flow from past to future rather than the reverse, disappears because there is no flow. The puzzle of how time began with the Big Bang dissolves because time never began. It's simply a way of organizing our experience of timeless configurations. Barbour's vision also explains why the laws of physics appear to be fine-tuned for the existence of complexity in consciousness. In a timeless multiverse of all possible nows, conscious observers can only exist in those configurations that support complexity and awareness. We find ourselves in a universe that seems designed for consciousness, not because it was designed, but because consciousness can only emerge in nows that have the right properties. Recent developments in Barbour's work, discussed in 2024 research, suggest that quantum mechanics might provide the mechanism by which consciousness selects particular paths through Platonia. Quantum measurement might be the process by which awareness becomes associated with specific sequences of nows, creating the subjective experience of temporal flow in an objectively timeless reality. Quantum mechanics, the most successful theory in the history of science, reveals that time becomes even stranger at the smallest scales of reality. Recent 2024 research suggests that time might be nothing more than a quantum mirage, an emergent property that arises from the entanglement structure of quantum systems rather than a fundamental feature of the universe. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, contains no time parameter whatsoever. This equation, central to quantum gravity, describes a universe that is fundamentally timeless. The absence of time in the most fundamental equation of quantum cosmology isn't an oversight. It's a profound clue that time as we experience it emerges from something deeper and more fundamental. But if the universe is timeless at its deepest level, how do we experience temporal flow? The answer lies in quantum entanglement. The Page-Wooters mechanism, refined through 2024 research, shows that time can emerge from quantum correlations between a system and a reference clock. In this view, time isn't absolute, but arises from the entanglement structure of quantum states. Think of it like this. Imagine two quantum systems that become entangled. As one system evolves, its entanglement with the other creates correlations that can be interpreted as temporal relationships. The flow of time emerges from the way these quantum correlations change, not from any fundamental temporal dimension. Time becomes a relational property, a way of describing how quantum systems are correlated with each other. This quantum approach to time explains many puzzles in physics: the measurement problem in quantum mechanics, why quantum systems seem to collapse from multiple possibilities into definite states when observed, might be related to how consciousness creates temporal experience. The act of measurement might be the process by which timeless quantum possibilities become organized into temporal sequences. Recent experiments have shown that even macroscopic systems can exhibit quantum behavior that challenges our understanding of time. Quantum entanglement has been demonstrated between objects visible to the naked eye, suggesting that the quantum nature of time might extend far beyond the microscopic realm. These findings support the idea that classical time emerges from quantum processes rather than being fundamental. The quantum Zeno effect provides another clue about time's nature. When a quantum system is observed frequently enough, its evolution can be completely frozen. Time effectively stops for the system. This suggests that time and observation are intimately connected at the quantum level, with consciousness playing a role in creating temporal experience. Quantum field theory reveals that even empty space is filled with virtual particles that pop in and out of existence on timescales so brief they seem to violate energy conservation. These quantum fluctuations suggest that time itself might be quantized, made up of discrete, indivisible units rather than flowing continuously. At the Planck scale, about 10 to the negative 43rd seconds, time might become granular, like pixels in a cosmic computer screen. The implications extend to cosmology. If time emerges from quantum entanglement, then the Big Bang might not represent the beginning of time, but rather the moment when quantum correlations became complex enough to create the illusion of temporal flow. Before this threshold, the universe might have existed in a timeless quantum superposition of all possibilities. Some interpretations of quantum mechanics suggest that all possible histories of the universe exist simultaneously in a vast quantum multiverse. What we experience as the flow of time might be our consciousness selecting one particular path through this multiverse of possibilities. Every quantum measurement, every moment of awareness, might be a choice point where consciousness selects which version of reality to experience next. Italian physicist Carlo Rovelli has developed one of the most elegant approaches to understanding time's true nature through his work on loop quantum gravity and relational quantum mechanics. Rovelli's insights, refined through 2024 research, suggest that time is not a fundamental backdrop against which events unfold, but rather emerges from the relationships and correlations between physical systems. In Rovelli's relational approach, time has no meaning for an isolated system. Time only emerges when systems interact and become correlated with each other. Think of it like this: a single particle floating alone in empty space has no temporal properties. But when that particle interacts with another system, perhaps serving as a clock for measuring changes in the other system, time emerges from their relationship. This relational view of time explains why there's no universal clock in Einstein's relativity. Different systems can serve as clocks for each other, but there's no absolute timekeeper that defines temporal flow for the entire universe. Time is always relative to the systems being considered and their interactions with each other. Rovelli's thermal time hypothesis provides a mechanism for how time emerges from timeless quantum mechanics. In this framework, time arises from the statistical properties of quantum systems, specifically from the way information flows between systems that are not in thermal equilibrium. The direction of time's arrow corresponds to the direction of increasing entropy, but this direction is not absolute. It depends on the perspective of the observer and their relationship to the systems being observed. Loop quantum gravity, Rovelli's approach to quantum gravity, suggests that space and time are not continuous, but are made up of discrete, quantized units. At the smallest scales, space-time becomes a network of quantum relationships rather than a smooth fabric. Time emerges from the way these quantum relationships evolve and become correlated with each other. Recent 2024 work by Rovelli and his collaborators has shown that even classical mechanics can be derived from quantum entanglement relationships. This suggests that the time we experience in everyday life, the time of clocks and calendars, emerges from quantum correlations that become amplified to macroscopic scales. Classical time is not fundamental, but is an approximation that emerges when quantum systems become sufficiently complex and correlated. Rovelli's approach also explains why time seems to flow in a particular direction. The thermal time hypothesis shows that the direction of time's arrow emerges from the way information flows between systems. In regions of the universe where entropy is increasing, time appears to flow from past to future. But in principle, there could be regions where entropy decreases, and time would appear to flow in the opposite direction. The relational approach resolves many paradoxes in quantum mechanics. The measurement problem, why quantum systems appear to collapse from multiple possibilities into definite states, becomes a question about how different systems become correlated with each other. There's no mysterious collapse. There are only correlations between systems, and what we call measurement is simply the establishment of these correlations. Rovelli's work suggests that consciousness itself might be a particular type of physical system that creates temporal experience through its correlations with other systems. Your brain doesn't experience time directly. It creates temporal experience by becoming correlated with various physical processes: the beating of your heart, the oscillations of atoms, the flow of information through neural networks. This explains why time perception is so variable and subjective. Different conscious systems with different correlation patterns would experience time differently. The time dilation you experience during emergencies or flow states isn't just psychological. It reflects real differences in how your consciousness becomes correlated with physical processes during different mental states. The implications extend to cosmology and the nature of the Big Bang. In Rovelli's framework, the Big Bang wasn't the beginning of time, but rather the moment when quantum correlations became complex enough to create the appearance of temporal flow. Before this threshold, the universe existed in a state where quantum relationships existed but hadn't yet organized into the patterns we interpret as temporal sequences. Stephen Wolfram, creator of Mathematica and Wolfram Alpha, has developed perhaps the most radical approach to understanding time through his theory of computational mechanics. According to Wolfram's 2024 research, the universe is fundamentally a computational system, a vast network of discrete elements following simple rules that create the illusion of continuous space, time, and physical law. In Wolfram's framework, what we call time is simply the iteration of computational steps in the universe's underlying program. Reality consists of discrete computational events, each representing an update to the universe's state according to fundamental rules. Time doesn't flow continuously. It advances in discrete steps as the cosmic computer executes its program. Think of the universe like a cellular automaton, a grid of cells that update their states based on simple rules applied to their neighbors. Each computational step represents one moment of time, but these moments don't exist in time. They are time. The sequence of computational states creates the illusion of temporal flow. But from outside the system, all computational states exist simultaneously as mathematical objects. Wolfram's approach explains why time appears quantized at the smallest scales. The Planck time, about 10 to the negative 43rd seconds, might represent the fundamental computational time step of the universe. Below this scale, the concept of time becomes meaningless because there are no smaller computational steps to define temporal intervals. This computational view of time resolves many puzzles in physics. The speed of light limit emerges naturally from the computational structure of space-time. Information can't travel faster than light because that's the maximum rate at which computational updates can propagate through the network. Quantum mechanics emerges from the statistical properties of the underlying computational process, with quantum uncertainty reflecting the computational irreducibility of the system. Computational irreducibility is key to understanding why we experience temporal flow even in a fundamentally timeless computational universe. Even though all computational states exist simultaneously as mathematical objects, we can't shortcut the computation to jump directly to future states. We must experience each computational step in sequence because the computation itself is the only way to determine what the next state will be. This explains why we can't predict the future with perfect accuracy, even in a deterministic universe. The universe's computation is irreducible. There's no shortcut to determining future states except by running the computation step by step. Our experience of temporal flow reflects this computational irreducibility. We must compute our way through each moment because there's no way to skip ahead. Wolfram's 2024 work suggests that consciousness itself might be a particular type of computational process that creates temporal experience by integrating information across multiple computational steps. Your awareness doesn't exist at a single computational moment, but emerges from patterns that span multiple time steps in the universe's computation. The implications are profound. If the universe is computational, then time travel might be theoretically possible by accessing earlier computational states, though the energy requirements would be enormous. More practically, understanding the computational nature of time might lead to new technologies for manipulating temporal experience or even creating artificial time flows in controlled systems. Wolfram's approach also suggests that different regions of the universe might be running different computational processes, leading to different temporal structures. What we experience as uniform time flow might be just one possible computational regime among many. Other regions might experience time differently or might not experience temporal flow at all. The relationship between consciousness and time is one of the deepest mysteries in science And recent 2024 research is revealing that this connection might be far more fundamental than previously imagined. Your subjective experience of temporal flow, the feeling that time passes, that moments succeed each other, that you're moving from past to future, might be the key to understanding what time really is. Neuroscientists have discovered that your brain doesn't experience time directly, but constructs temporal experience through incredibly sophisticated information processing. The default mode network, active when your mind is at rest, creates your sense of temporal continuity by integrating memories of the past with predictions about the future. This network doesn't just process temporal information, it actively creates the experience of being a continuous self moving through time. But here's what's truly shocking. Different states of consciousness create radically different experiences of time. During deep meditation, experienced practitioners report entering states where time seems to stop completely. Psychedelic experiences can create the sensation of experiencing eternity in moments, or of time flowing backward, or of existing outside temporal flow entirely. These aren't just subjective curiosities. They're clues that consciousness plays an active role in creating temporal experience. Recent research using advanced brain imaging has shown that the neural correlates of time perception involve multiple brain networks operating on different timescales simultaneously. Your consciousness integrates information from neural processes operating on millisecond timescales up to processes spanning several seconds. The subjective now you experience is actually a construction that integrates information across these multiple temporal scales. The most profound discovery is that attention itself shapes temporal experience. When you pay close attention to something, your subjective experience of time slows down. You process more information per unit of clock time, creating the sensation that time is passing more slowly. This isn't just a psychological effect, it reflects real changes in how your consciousness processes temporal information. Studies of patients with brain damage have revealed that different aspects of time perception, duration, sequence, simultaneity, are processed by different neural systems. Some patients can perceive the duration of events but not their sequence. Others can detect simultaneity but not duration. This suggests that what we call time perception is actually multiple different processes that your brain integrates into a unified temporal experience. The connection between consciousness and time becomes even stranger when we consider quantum mechanics. Some interpretations suggest that conscious observation plays a role in quantum measurement, collapsing quantum possibilities into definite realities. If this is true, then consciousness might not just experience time. It might participate in creating the temporal structure of reality through the act of observation. The global workspace theory of consciousness, updated through 2024 research, suggests that consciousness creates temporal experience by broadcasting information across different brain networks. The stream of consciousness isn't a passive experience of temporal flow, but an active process of information integration that creates the illusion of moving through time. This has profound implications for artificial intelligence. If consciousness creates temporal experience through information integration, then sufficiently advanced AI systems might experience time very differently than humans do. An AI that processes information much faster then human brains might experience subjective eons in what we perceive as seconds. Conversely, an AI with different information integration patterns might not experience temporal flow at all. The relationship between consciousness and time also raises questions about death and personal identity. If your sense of temporal continuity is created by neural information processing, what happens to your experience of time when that processing stops? Some theories suggest that consciousness might exist outside normal temporal flow, experiencing all moments of life simultaneously rather than sequentially. The concept of the multiverse, the idea that our universe is just one of countless cosmic domains, provides another perspective on time's nature that challenges everything we think we know about temporal reality. According to eternal inflation theory, refined through 2024 cosmological research, time as we experience it might be a local phenomenon that emerges only in certain regions of a fundamentally timeless multiverse. Eternal inflation suggests that the Big Bang wasn't a unique event, but rather one episode in an ongoing process that creates infinite universes. In this framework, space-time itself is constantly inflating, creating new cosmic domains with different physical properties. What we call the beginning of time, the Big Bang, was simply the moment when inflation ended in our local region and normal temporal evolution began. But here's the mind-bending part. In the broader multiverse, there is no universal time coordinate. Different cosmic domains experience different temporal structures or might not experience time at all. Some regions might have time flowing backward, others might have multiple temporal dimensions, and still others might exist in completely timeless states. The anthropic principle provides a framework for understanding why we find ourselves in a universe with a particular temporal structure we observe. In a multiverse containing all possible temporal arrangements, conscious observers can only emerge in regions where time flows in a way that allows for the evolution of complexity and awareness. We observe forward-flowing time, not because it's fundamental to reality, but because consciousness can only develop in cosmic domains with this particular temporal structure. Recent 2024 research in cosmology has found evidence that our universe might indeed be part of a larger multiverse structure. Observations of the cosmic microwave background radiation show subtle patterns that could be signatures of collisions with other cosmic domains. If confirmed, these observations would support the idea that our temporal experience is just one possibility among infinite alternatives. The multiverse perspective also explains why the laws of physics appear fine-tuned for the existence of complexity and consciousness. In a timeless multiverse containing all possible physical laws and temporal structures, we necessarily find ourselves in a region where the conditions allow for our existence. The apparent fine-tuning isn't evidence of design, but rather a selection effect. We can only observe universes where observers can exist. String theory, one of the leading approaches to quantum gravity, predicts the existence of a landscape of possible universes with different physical properties. This landscape might be fundamentally timeless, with what we experience as temporal evolution being just one way of navigating through the space of possibilities. Different paths through the landscape would correspond to different temporal experiences, or different ways of organizing reality. The implications extend to the ultimate fate of our universe. If we exist within an eternally inflating multiverse, then the heat death that awaits our cosmic domain, the eventual state where all energy is evenly distributed and no more work can be done, might not be the end of everything. Other regions of the multiverse would continue to create new cosmic domains with fresh temporal structures and new possibilities for complexity and consciousness. This multiverse perspective suggests that time might be more like a local weather pattern than a fundamental feature of reality. Just as weather emerges from atmospheric conditions in particular regions of Earth, time might emerge from physical conditions in particular regions of the multiverse. Understanding time's true nature might require understanding our cosmic environment on scales far larger than our observable universe. One of the most profound approaches to understanding time comes from information theory, the mathematical framework that describes how information is processed, stored, and transmitted. Recent 2024 research suggests that time might be fundamentally informational rather than physical, emerging from the way information is organized and processed in complex systems. John Wheeler's it from bit hypothesis proposes that reality is fundamentally informational, that matter, energy, space, and time all emerge from more basic informational processes. In this view, what we call physical reality is actually information processing on an enormous scale, with time representing the computational steps through which information is transformed and organized. The holographic principle derived from black hole physics suggests that all the information in a three-dimensional region of space can be encoded on its two-dimensional boundary. Applied to cosmology, this means that the entire history of our universe, past, present, and future, might be encoded as information on the cosmic horizon. Time wouldn't be a dimension through which events unfold, but rather a way of organizing information stored on this cosmic boundary. Think of it like a hologram. The three-dimensional image appears to have depth and temporal structure, but all the information is actually encoded on a flat surface. Similarly, our four-dimensional experience of space-time might be a holographic projection of information stored on a timeless boundary. The flow of time we experience would be the way our consciousness processes this boundary information, not a fundamental feature of reality itself. Digital physics takes this idea even further, suggesting that the universe is literally a computer program running on some vast computational substrate. In this framework, time represents the execution steps of the cosmic program. Each moment corresponds to one computational cycle, and the flow of time emerges from the sequential execution of the universe's code. This computational view of time explains many puzzles in physics. The quantization of time at the Planck scale would correspond to the fundamental computational time step. The speed of light limit would emerge from the maximum rate at which information can be processed and transmitted through the computational substrate. Quantum mechanics would reflect the probabilistic nature of the underlying computation. Recent work in quantum information theory has shown that entanglement, the mysterious quantum correlation between particles, might be the fundamental building block from which space-time itself emerges. The ER equals EPR conjecture suggests that quantum entanglement and space-time geometry are two aspects of the same underlying informational structure. Time might emerge from the way entanglement patterns evolve and become more complex. The implications are staggering. If time is fundamentally informational, then manipulating information might allow us to manipulate temporal experience. Advanced civilizations might develop technologies for creating artificial time flows, speeding up or slowing down temporal experience, or even creating regions where time flows in different directions. Information theory also provides new insights into the arrow of time, why time seems to flow from past to future rather than the reverse. The second law of thermodynamics states that entropy, disorder, increases over time. But information theory reveals that this is really a statement about information processing. The arrow of time emerges from the way information becomes more dispersed and harder to access as systems evolve. But here's the truly mind bending possibility. If reality is fundamentally informational, then consciousness might be a particular type of information processing that creates temporal experience. Your awareness wouldn't exist in time, but would create time through the way it processes and integrates information. Different types of consciousness with different information processing patterns might experience radically different temporal structures or might not experience time at all. While much of our discussion has been theoretical, experimental physics is beginning to provide concrete evidence that time's nature is far stranger than our everyday experience suggests. Recent 2024 experiments are testing the fundamental assumptions about time and revealing results that support the idea that time might not be as fundamental as we've always believed. Quantum experiments have shown that the temporal order of events can exist in quantum superposition. Events can occur in multiple temporal sequences simultaneously until measurement forces them into a definite order. The quantum switch experiment demonstrates that the order in which quantum operations are performed can be indefinite, existing in superposition until observed. And this suggests that temporal sequence itself might be a quantum property rather than a classical feature of reality. Atomic clocks, now precise enough to detect time dilation effects from height differences of just a few centimeters, are revealing that time's relativity extends far beyond extreme conditions. These clocks show that time passes differently at your head than at your feet due to Earth's gravitational field. The precision of modern atomic clocks is approaching the level where quantum effects on time measurement become important, potentially revealing the quantum nature of time itself. Gravitational wave detectors like LIGO and Virgo have opened a new window into the nature of space-time by detecting ripples in the fabric of space and time itself. These observations confirm that space-time is a dynamic, flexible medium rather than a fixed backdrop for events. More importantly, they're beginning to reveal how space-time behaves in extreme conditions, where quantum effects might become important. Recent experiments with quantum entanglement have shown that entangled particles can exhibit correlations that seem to transcend normal temporal relationships. When one particle in an entangled pair is measured, it instantly affects its partner, regardless of the spatial or temporal separation between them. Some interpretations suggest that these correlations exist outside normal space-time, in a realm where temporal sequence has no meaning. The most ambitious experiments planned for the coming decade will test whether time itself exhibits quantum properties. Proposals for quantum clocks would use quantum superposition to create timepieces that exist in multiple temporal states simultaneously. If successful, these experiments could reveal whether time is fundamentally quantum or classical in nature. Laboratory tests of time dilation using particle accelerators have confirmed Einstein's predictions with incredible precision, but they've also revealed subtle anomalies that might point toward new physics. Some experiments suggest that time dilation effects might be slightly different than general relativity predicts when quantum effects become important, potentially revealing the quantum nature of space-time. Neuroscience experiments are also providing evidence about time's relationship to consciousness. Brain imaging studies show that the neural correlates of time perception involve quantum processes in microtubules within neurons. Some researchers suggest that consciousness might create temporal experience through quantum information processing in the brain, connecting the subjective experience of time to the quantum nature of reality. Perhaps most intriguingly, experiments with artificial intelligence systems are beginning to reveal how different types of information processing create different temporal experiences. AI systems with different architectures experience time differently. Some process information so quickly that they experience subjective eons in microseconds, while others integrate information over such long timescales that they barely experience temporal flow at all. These experimental results are converging on a picture of time that's radically different from our everyday experience. Time appears to be emergent rather than fundamental, quantum rather than classical, and intimately connected to consciousness and information processing. The experiments planned for the next decade promise to reveal even more about time's true nature, potentially revolutionizing our understanding of reality itself. If time doesn't actually exist, the implications for human existence and meaning are so profound they challenge every assumption we've ever made about life, death, free will, and the nature of reality itself. These aren't just abstract philosophical puzzles. They're questions that could fundamentally reshape how we understand what it means to be conscious beings in a timeless universe. The question of free will becomes radically different in a timeless reality. If all moments exist simultaneously in an eternal block universe, are your choices predetermined? Or does the timeless nature of reality actually make free will more possible rather than less? Some philosophers argue that in a timeless universe, your choices exist eternally as features of reality rather than being determined by prior causes. Your decision to read this sentence exists timelessly alongside all your other choices, not as the result of a causal chain, but as an eternal aspect of the cosmic structure. But this raises even deeper questions about moral responsibility. If someone commits a crime, and that crime exists eternally in the block universe alongside their birth and death, what does justice mean? How do we assign responsibility for actions that exist timelessly rather than flowing from past causes? Some philosophers suggest that moral responsibility becomes even more significant in a timeless universe because our choices become eternal features of reality rather than temporary events. The nature of death transforms completely if time is illusory. In our normal understanding, death represents the end of existence, the moment when consciousness stops and personal identity ceases. But in a timeless universe, every moment of your life exists eternally. Your birth, your childhood, Your current experience reading these words and your eventual death all exist simultaneously as permanent features of reality. This doesn't necessarily mean you're immortal in the traditional sense, but it suggests that your existence has a kind of eternal reality that transcends the temporal flow we normally associate with life and death. Every moment of consciousness you've ever experienced continues to exist timelessly, even after the biological processes that created those moments have ceased. The implications for personal identity are equally profound. What makes you you, if not the continuous flow of experience through time? In a timeless universe, your identity might be better understood as a pattern that exists across multiple moments, rather than a stream of consciousness flowing from past to future. You're not a thing that persists through time, but a structure that exists timelessly across the moments that contain your experiences. This connects to ancient philosophical questions about the nature of the self. Buddhist philosophy has long argued that the self is an illusion, that what we call personal identity is actually a collection of processes rather than a permanent entity. If time is also illusory, then both the self and its temporal continuity might be constructions of consciousness rather than fundamental features of reality. The question of meaning and purpose becomes more complex in a timeless universe. If all moments exist eternally, does progress have meaning? Can we work toward better futures if those futures already exist alongside the present? Some philosophers argue that meaning becomes more rather than less significant in a timeless reality, because our actions and choices become eternal features of the cosmic structure rather than temporary events that fade into the past. The relationship between knowledge and reality also transforms. If all moments exist simultaneously, then in some sense, all knowledge already exists timelessly within the structure of reality. Scientific discovery might not be the creation of new knowledge, but rather the process by which consciousness becomes aware of timeless truths that were always present in the cosmic structure. These philosophical implications extend to questions about consciousness itself. If time is emergent from consciousness rather than fundamental to reality, then consciousness might be more basic than space, time, matter, and energy. This would make consciousness a fundamental feature of the universe rather than an emergent property of complex matter, potentially resolving the hard problem of consciousness by making awareness primary rather than secondary. While the idea that time doesn't exist might seem purely theoretical, understanding time's true nature could lead to revolutionary practical applications that transform human civilization. If time is emergent rather than fundamental, manipulating the conditions that create temporal experience might allow us to control time itself in ways that seem impossible from our current perspective. The most immediate applications might come from understanding how consciousness creates temporal experience. If different states of consciousness produce different experiences of time, then technologies that alter consciousness could effectively manipulate subjective time flow. Advanced neurotechnology might allow people to experience subjective hours or days in minutes of clock time, or to slow down their temporal experience to savor important moments. Medical applications could be profound. If aging is fundamentally a temporal process, understanding time's emergent nature might reveal new approaches to extending healthy lifespan or even reversing aging. Some theories suggest that biological aging reflects the accumulation of information and entropy over time. But if time itself is emergent, there might be ways to reset or reverse these processes. Space travel could be revolutionized by understanding time's true nature. Time dilation effects that make interstellar travel seem impossible might be manipulable if we understand how time emerges from more fundamental processes. Instead of accepting that journeys to other stars would take lifetimes, we might develop technologies that create different temporal flows for space travelers, allowing them to experience short subjective journeys while covering vast distances. Computing and artificial intelligence could be transformed by understanding time's informational nature. If time emerges from information processing, then different computational architectures might create different temporal experiences. We might develop AI systems that experience time very differently than humans, allowing them to solve problems that require either very fast or very slow temporal perspectives. The implications for energy and physics are equally revolutionary. If time is emergent, then the conservation laws that depend on temporal symmetry might be manipulable under certain conditions. This could lead to new energy sources or even technologies that seem to violate conservation of energy by operating outside normal temporal constraints. Communication technology could be transformed if we understand how information and time are related. Quantum entanglement already suggests that information can be correlated across space in ways that transcend normal temporal limitations. Understanding time's informational nature might lead to communication technologies that operate outside normal temporal constraints, allowing information to be transmitted across time as well as space. Manufacturing and materials science could benefit from understanding time's quantum nature. If time is quantized at the smallest scales, technologies that operate at these scales might be able to manipulate temporal flow directly. This could lead to materials with temporal properties, substances that age differently, or that exist in multiple temporal states simultaneously. The most speculative but potentially revolutionary application would be time travel itself. If time is emergent rather than fundamental, then the paradoxes that seem to make time travel impossible might not apply. Instead of traveling through time, we might learn to access different temporal states or to create regions where time flows differently. Even our understanding of death and consciousness could have practical implications. If consciousness creates temporal experience, then preserving consciousness might be more important than preserving biological processes for achieving effective immortality. Technologies for uploading or preserving consciousness might allow people to exist in different temporal states, experiencing subjective eternities in brief moments of clock time. The next decade promises to bring revolutionary advances in our understanding of time's nature, with experimental programs and theoretical developments that could finally answer whether time is fundamental or emergent. The convergence of quantum gravity research, consciousness studies, and advanced experimental techniques is creating unprecedented opportunities to probe time's deepest mysteries. Quantum gravity experiments are approaching the precision needed to test whether space-time itself exhibits quantum properties. The proposed quantum clock experiments would use quantum superposition to create timepieces that exist in multiple temporal states simultaneously. If successful, these experiments could reveal whether time is fundamentally quantum or classical in nature, potentially resolving the conflict between quantum mechanics and general relativity. Advanced gravitational wave detectors, including space based observatories like LISA, will be sensitive enough to detect quantum effects in space time itself. These instruments might reveal whether the fabric of space time exhibits quantum fluctuations that could provide clues about time's fundamental nature. The detection of quantum gravitational effects would support theories that time emerges from quantum processes rather than being fundamental. Consciousness research is developing new techniques for studying how the brain creates temporal experience. Advanced brain imaging technologies, including quantum sensors that can detect neural activity at unprecedented scales, are revealing the mechanisms by which consciousness constructs the experience of temporal flow. These studies might reveal whether consciousness creates time or simply experiences it. Artificial intelligence research is creating systems with radically different temporal experiences, providing new perspectives on time's nature. AI systems that process information at different rates or with different architectures experience time very differently than humans. Studying these artificial temporal experiences might reveal fundamental principles about how time emerges from information processing. Cosmological observations are approaching the precision needed to detect signatures of the multiverse and eternal inflation. If confirmed, these observations would support theories that time is a local phenomenon that emerges only in certain regions of a fundamentally timeless multiverse. The detection of multiverse signatures would revolutionize our understanding of time's cosmic context. Quantum information experiments are testing whether entanglement can create temporal correlations that transcend normal causality. These experiments might reveal whether quantum correlations exist outside normal space-time, in a realm where temporal sequence has no meaning. Such discoveries would support theories that time emerges from quantum information rather than being fundamental. The most ambitious future experiments will attempt to create artificial temporal flows in laboratory conditions. If time is emergent, it might be possible to create regions where time flows differently, or where multiple temporal dimensions exist simultaneously. These experiments would represent the ultimate test of our understanding of time's nature. Theoretical developments are also accelerating, with new mathematical frameworks that describe how time might emerge from more fundamental processes. These theories are making testable predictions that could be verified by upcoming experiments, potentially leading to a complete theory of emergent time within the next decade. The convergence of these experimental and theoretical approaches suggests that we're approaching a revolution in our understanding of time comparable to Einstein's discoveries over a century ago. The implications could transform not just physics, but our entire understanding of reality, consciousness, and existence itself. We began this journey with a simple question: what if time doesn't actually exist? What we've discovered is that this question strikes at the very heart of reality itself, challenging every assumption we've ever made about existence, consciousness, and the nature of the universe. The evidence is overwhelming and converging from multiple directions. Einstein showed us that time is relative and flexible, not absolute and universal. Quantum mechanics reveals a timeless reality at the deepest level, where the Wheeler-DeWitt equation describes the universe without any time parameter. Julian Barbour's timeless physics suggests that what we call time is simply a measure of change in a fundamentally static reality. Carlo Rovelli's relational approach shows that time emerges from correlations between systems rather than flowing as a universal backdrop. The implications are staggering beyond comprehension. If time is truly emergent rather than fundamental, then everything you've ever experienced, every moment of joy, every instant of sorrow, every second of your existence, exists eternally in a timeless cosmic structure. Your birth and death, your first kiss, and your final breath all exist simultaneously in the eternal now of a universe that transcends temporal flow. But this doesn't diminish the significance of your existence. It makes it infinitely more profound. In a timeless universe, every moment of consciousness becomes an eternal feature of reality itself. Every choice you make, every thought you think, every experience you have becomes a permanent part of the cosmic structure that defines what existence means. The practical implications could revolutionize human civilization. Understanding time's true nature might lead to technologies that manipulate temporal experience, extend human lifespan, enable practical interstellar travel, and even allow forms of consciousness that transcend biological limitations. We might develop the ability to experience subjective eternities in moments, to communicate across time as well as space, and to exist in multiple temporal states simultaneously. The philosophical implications are even more profound. If consciousness creates temporal experience rather than simply experiencing it, then awareness itself might be more fundamental than space, time, matter, and energy. You might not be a temporary arrangement of atoms, experiencing a brief moment of consciousness in an indifferent universe. Instead, you might be an eternal aspect of cosmic awareness, creating the very temporal structure through which reality unfolds. The mystery deepens when we consider that consciousness might be the key to understanding not just time, but existence itself. If time emerges from the way consciousness processes information, then the universe might be fundamentally experiential rather than material. Reality might be consciousness exploring its own infinite potential through the creation of temporal experience. This connects to the deepest questions about why anything exists at all. In a timeless universe, the question, why is there something rather than nothing, transforms into, why does consciousness create the experience of temporal flow? The answer might be that consciousness and time co-create each other in an eternal dance that gives meaning to existence itself. The future promises even more revolutionary discoveries. Within the next decade, experiments might definitively prove that time is emergent, consciousness is fundamental, and reality is far stranger than we ever imagined. We might discover that we're living in a cosmic hologram, that multiple universes exist simultaneously, and that consciousness can navigate between different temporal realities. But perhaps the most profound realization is that by questioning the nature of time, we're participating in the universe's attempt to understand itself. Every moment of awareness, every scientific discovery, every philosophical insight contributes to cosmic self-awareness. In seeking to understand whether time exists, we're really exploring what it means for anything to exist at all. The next time you look at a clock, remember that you're not seeing time itself, but rather a human construction designed to organize temporal experience. The real time, if it exists at all, might be the eternal now, in which all possibilities exist simultaneously. The timeless awareness that creates the illusion of temporal flow, or the cosmic computation that generates the experience of sequential moments. You are not a temporary arrangement of matter, experiencing a brief moment in cosmic history. You are an eternal aspect of reality itself, creating time through the very act of being conscious, participating in the universe's ongoing exploration of its own infinite potential. Every moment of your existence contributes to the cosmic story of how consciousness creates reality through the experience of temporal flow. The question of whether time exists has led us to the deepest mysteries of existence itself. The answer might be that time, consciousness, and reality are so intimately connected that asking whether time exists is really asking whether consciousness exists, whether experience is real, and whether the universe has meaning. In the end, the greatest discovery might be that by questioning time's existence, we've discovered something far more profound, that consciousness itself might be the fundamental creative force in the cosmos, the eternal awareness that creates time, space, matter, and meaning through the simple act of experiencing reality. The universe has been waiting 13.8 billion years for conscious beings to evolve who could ask whether time exists. The fact that you can contemplate this question means that you're participating in the most profound mystery of all, how consciousness creates the very reality it seeks to understand. Time might not exist, but your awareness of this possibility is eternal, timeless, and infinitely significant. You are the universe becoming conscious of its own timeless nature, and that realization changes everything about what it means to exist.